Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The convergence of statistical modelling and artificial intelligence witnessed a pivotal moment with the emergence of the hierarchical mixtures of experts architecture, a concept articulated definitively in the 1985 paper Hierarchical Mixtures of Experts and the EM Algorithm by Michael I. Jordan, Robert Jacobs, and John S. Polak. This paper, beyond its technical contributions, presented a paradigm shift in approaching complex learning problems by decomposing them into simpler, more manageable subproblems. This essay undertakes a critical evaluation of the claims and arguments presented within this seminal work, dissecting its methodology, assumptions, and implications to illuminate its enduring significance. The analysis proceeds section by section, delving into the core tenets of the hierarchical mixtures of experts framework and the application of the expectation maximization algorithm for parameter estimation. Section 1 Introduction to Mixtures of Experts and the Problem Setting. The introductory section of the Jordan, Jacobs and Polak paper lays out the fundamental motivation behind the mixtures of experts approach. It acknowledges the limitations of traditional single-model approaches when confronted with data exhibiting significant heterogeneity or non-stationarity. Such data challenges the ability of a single model to capture the underlying relationships effectively. The paper proposes a modular architecture, where the learning task is divided among several expert models, each specializing in a particular region of the input space. A gating network dynamically mediates the contributions of these experts, effectively implementing a form of adaptive model selection. The core claim here is that this divide-and-conquer strategy allows for a more flexible and accurate representation of complex data compared to monolithic models. This claim, while intuitive, hinges heavily on the appropriate selection of experts and the effectiveness of the gating network in properly partitioning the input space. The introduction implicitly assumes the existence of separable regions in the data, an assumption which, if violated, could render the mixtures of experts approach less advantageous. The authors suggest the advantage of mixtures of experts lies in the ability to learn complex, non-linear mappings by combining simpler linear models. This is a crucial point, as it frames the approach as a means of achieving expressive power through modularity rather than relying on complex individual models. Section 2 Expectation maximization algorithm for parameter estimation. The paper dedicates a significant portion to detailing the application of the expectation maximization, abbreviated EM, algorithm for estimating the parameters of the mixtures of experts model. The EM algorithm is particularly well suited to problems involving latent variables. In this case, the assignment of data points to specific experts. The authors carefully lay out the two steps that comprise the EM algorithm: the expectation step, where the posterior probabilities of expert assignments are computed given the current parameter estimates, and the maximization step, where the parameters of both the experts and the gating network are updated to maximize the expected complete data log likelihood. This process is iterated until convergence. A central claim within this section is that the EM algorithm provides a principled and convenient method for parameter estimation in the mixtures of experts framework. The authors suggest that the iterative nature of the EM algorithm allows for a gradual refinement of the model parameters, leading to improved performance. However, the EM algorithm is known to be susceptible to local optima, which can significantly hinder its performance. The paper acknowledges this limitation implicitly, suggesting that careful initialization of the parameters is crucial for achieving satisfactory results. The authors also assume that the likelihood function is well behaved, exhibiting sufficient regularity, properties to ensure the convergence of the EM algorithm. This assumption might not always hold in practice, especially when dealing with complex data. Careful consideration of the data characteristics is therefore important when applying the EM algorithm to train mixture of experts models. Specifically, The S-step involves computing the posterior probability, conditioned on the parameters of the experts and the gating network, of each data point belonging to each expert. The M-step then maximizes the expected complete data log likelihood, which leads to update equations for the parameters of both the experts and the gating network. The authors assert that these update equations are tractable, allowing for efficient computation of the parameter estimates. Section 3. The hierarchical extension to mixtures of experts. The core innovative contribution of the Jordan, Jacobs, and Polak paper lies in the introduction of a hierarchical extension to the basic mixtures of experts architecture, building upon the conventional mixtures of experts architecture, with one layer of experts and one gating network. The authors introduce a recursively structured architecture, where gating networks themselves are replaced by other mixtures of experts. This hierarchical structure allows for a refined and more nuanced partitioning of the input space. A key claim here is that the hierarchical structure enables the model to capture more complex relationships in the data that cannot be captured by a single layer of experts. The authors suggest that the hierarchical structure allows the model to learn representations at different levels of abstraction, with lower levels capturing fine-grained details and higher levels capturing more global patterns. The authors specifically claim that this architecture allows for the representation of complex, non-linear mappings by decomposing them into a series of simpler, locally linear mappings. This claim depends critically on the effectiveness of the hierarchical decomposition in properly partitioning the input space at each level of the hierarchy. The authors emphasize the scalability benefits of the hierarchical structure, arguing that it allows for the construction of models with a large number of experts without incurring excessive computational costs. This benefit stems from the fact that the gating networks at each level of the hierarchy only need to consider a subset of the experts, reducing the overall computational complexity. The architecture's ability to model context-sensitive input-output relationships, and specifically the claim that the hierarchical extension offers greater flexibility, relies on the modular structure of the network. By allowing for local specialization of the expert gating networks to learn the relevance of such experts within local regions of the input space, a more nuanced and data-adaptive model can be developed. Section 4. Derivation of the EM algorithm for hierarchical mixtures of experts. The paper provides a detailed derivation of the expectation maximization algorithm for the hierarchical mixtures of experts model. The derivation extends the basic EM algorithm to account for the multiple levels of gating networks in the hierarchy. The authors meticulously present the update equations for the parameters of the experts and the gating networks at each level. A key claim here is that the EM algorithm can be readily adapted to the hierarchical structure, providing a principled and efficient method for parameter estimation. The authors demonstrate that the update equations for the hierarchical model have a similar form to those for the basic model, allowing for reuse of existing code and computational infrastructure. The authors emphasize the importance of proper normalization of the posterior probabilities at each level of the hierarchy, ensuring that the probabilities sum to 1 and that the algorithm converges to a valid solution. The derivation hinges on the assumption that the conditional distributions of the outputs given the inputs and the expert assignments are well defined. These distributions are typically assumed to be Gaussian, but other distributions could be used depending on the nature of the data. The authors claim that the EM algorithm provides a consistent and unbiased estimate of the model parameters, provided that the model structure is correctly specified and that the data are sufficiently informative. Section 5. Experimental results and evaluation. The paper presents experimental results to evaluate the performance of the hierarchical mixtures of experts model on several benchmark datasets. These experiments serve as an instantiation of the theoretical framework discussed earlier. The authors compare the performance of the hierarchical model to that of a single-layer mixtures of experts model and other traditional machine learning algorithms. The central claim here is that the hierarchical model outperforms the other algorithms on complex learning tasks, demonstrating the benefits of the hierarchical structure. The experimental results support this claim, Showcasing superior accuracy and generalization performance for the hierarchical model, the authors explore the sensitivity of the model to various parameters, such as the number of experts at each level and the learning rate of the EHM algorithm. They suggest that the model is relatively robust to these parameters, indicating that it can be applied to a wide range of problems without requiring extensive parameter tuning. A critical aspect of the experimental evaluation is the choice of data sets. The paper selects data sets that exhibit significant heterogeneity or non-stationarity, which are precisely the types of problems that the mixtures of experts approach is designed to address. The authors provide a detailed description of the experimental setup, including the data preprocessing steps, the parameter initialization strategies, and the evaluation metrics used. The authors present a statistical analysis of the results, demonstrating that the improvements achieved by the hierarchical model are statistically significant. The authors explicitly claim the EM algorithm provides reliable parameter estimates of their experiments support. Section 6 analysis of the model's strengths and limitations beyond the specific experimental results. The paper offers a more general analysis of the strengths and limitations of the hierarchical mixtures of experts model. The authors highlight the model's ability to capture complex relationships in the data through its hierarchical structure and adaptive model selection mechanism. They also acknowledge the model's susceptibility to local optima and the computational cost associated with training larger-scale models. A key claim here is that the model represents a powerful tool for addressing complex learning problems, but it requires careful consideration of its limitations and appropriate application techniques. The authors suggest that the model is particularly well suited to problems where the data can be naturally decomposed into a hierarchy of subproblems. They also caution against overfitting, recommending the use of regularization techniques to prevent the model from memorizing the training data. The authors speculate on the potential for extending the model to handle more complex data types, such as images and text. They also discuss the possibility of integrating the model with other machine learning algorithms, such as deep neural networks. The authors offer practical guidance on how to choose the appropriate model architecture and training parameters for a given learning task. They emphasize the importance of data exploration and visualization in understanding the underlying structure of the data and informing the model design process. The authors identify hyperparameter sensitivity as a model limitation and acknowledge that careful adjustment may be required depending on the exact nature of the dataset being employed. The authors do note that their experiments show the model is relatively robust, but this is not to say that hyperparameter tuning can be ignored. Section 7 Impact and Influence of the 1985 paper. The 1985 George Jacobs and Polak paper proved to be a highly influential work, shaping subsequent research in the fields of machine learning, neural networks, and statistical modeling. The paper's introduction of the hierarchical mixtures of experts architecture sparked considerable interest in modular learning approaches, leading to the development of numerous variations and extensions of the original model. A key claim here is that the paper laid the foundation for a new paradigm in machine learning, one that emphasizes modularity, adaptivity, and hierarchical representation. The paper's use of the expectation maximization algorithm for parameter estimation had a significant impact on the development of efficient training algorithms for complex models. The paper's insights into the benefits of adaptive model selection have informed the design of various adaptive algorithms, such as boosting and bagging. The hierarchical mixtures of experts model has been applied to a wide range of problems, including speech recognition, image classification, and financial forecasting. The paper has been cited extensively in the academic literature, solidifying its status as a seminal work in the field. The paper's impact extends beyond the immediate field of machine learning, influencing research in cognitive science, neuroscience, and control theory. This highlights the interdisciplinary nature of the work and its relevance to a broad range of scientific disciplines. The paper's emphasis on modularity and adaptability has resonated with researchers interested in building intelligent systems that can operate in complex and dynamic environments. Subsequent research focused on addressing some of the limitations of the original model, such as its susceptibility to local optima and its computational cost. Researchers have developed various techniques for improving the performance and scalability of hierarchical mixtures of experts models, including the use of stochastic gradient descent and distributed computing. Section 8. The relationship to later mixture model research. The foundational concepts introduced in the 1985 paper by Jordan, Jacobs and Polak bear a discernible relationship to the broader landscape of mixture model research that unfolded subsequently. The paper's emphasis on partitioning the input space and utilizing multiple experts to address different regions anticipates later developments in areas such as ensemble learning and deep learning. The key claim here is that the paper established a cornerstone for future research in which ensembles of models would be combined to achieve superior performance compared to single models. The paper's focus on the expectation maximization algorithm highlights the importance of iterative optimization techniques for estimating the parameters of complex statistical models, a theme that continues to be central to present-day machine learning research. The hierarchical structure introduced in the paper anticipates later work on deep neural networks, which also leverage hierarchical representations to capture complex patterns in data. The author's emphasis on the modularity of the architecture foreshadows later developments in areas such as transfer learning and meta-learning, where models trained on one task are adapted to perform well on other related tasks. The paper's insights into the benefits of adaptive model selection have informed the design of various adaptive learning algorithms, such as reinforcement learning algorithms, that adapt their behavior based on the observed environment. Subsequent research has explored various extensions of the hierarchical mixtures of experts model, such as the use of non-parametric experts and the incorporation of Bayesian inference techniques. These extensions have further expanded the applicability of the model to a wider range of problems. The authors showed the importance of both local expertise and global coordination in complex learning tasks. The architecture established here has provided a powerful framework for addressing complex problems and continues to inspire new research directions. Section 9. Contemporary significance and future directions. Despite its publication several decades ago, the 1985 paper by Jordan, Jacobs, and Polak retains significant relevance in contemporary machine learning. The hierarchical mixtures of experts architecture remains a valuable tool for addressing complex learning problems, and the expectation maximization algorithm continues to be widely used for parameter estimation. A key claim here is that the fundamental principles articulated in the paper remain applicable to modern machine learning challenges, such as those arising in the fields of deep learning and artificial intelligence. The paper's emphasis on modularity and adaptivity aligns well with the current trend toward building intelligent systems that can operate in complex and dynamic environments. The paper's insights into the benefits of hierarchical representation have influenced the design of deep neural networks, which also leverage hierarchical structures to capture complex patterns in data. The paper's focus on the expectation maximization algorithm has informed the development of various optimization algorithms used to train deep learning models. A hierarchical mixtures of experts model can be seen as a precursor to modern ensemble learning techniques, such as boosting and bagging, which also combine multiple models to achieve superior performance. The paper's legacy extends beyond the immediate field of machine learning, influencing research in areas such as cognitive science, neuroscience, and control theory. Future research directions could explore the integration of hierarchical mixtures of experts models with other machine learning algorithms, such as deep neural networks and reinforcement learning algorithms. Researchers could also investigate the use of non-parametric experts and Bayesian inference techniques to further enhance the flexibility and robustness of the model. The model continues to offer a rich and fertile ground for future research and development, continuing to provide valuable insights into the design of intelligent systems. Section 10 Conclusion Enduring Value of the HME Framework. In conclusion, the 1985 paper Hierarchical Mixtures of Experts and the EDM Algorithm represents a seminal contribution to the fields of machine learning and artificial intelligence. The paper's introduction of the hierarchical mixtures of experts architecture and its application of the expectation maximization algorithm laid the foundation for a new paradigm in machine learning, one that emphasizes modularity, adaptivity, and hierarchical representation. The paper's enduring value lies in its ability to provide a principled and effective framework for addressing complex learning problems. The paper's insights into the benefits of adaptive model selection and hierarchical representation have had a profound impact on subsequent research. The paper's legacy extends beyond the immediate field of machine learning, influencing research in areas such as cognitive science, neuroscience, and control theory. The hierarchical mixtures of experts model continues to offer a rich and fertile ground for future research and development, promising to provide valuable insight into the design of intelligent systems for years to come. The work's impact is not merely historical, its principles related to modularity and adaptive expertise remain powerfully relevant. Indeed, the idea of decomposing a complex problem into simpler, specialized components, guided by a higher-level structure, persists as a core motif in modern artificial intelligence research, attesting to the foresight and lasting significance of Jordan, Jacobs, and Polak's contribution. The authors successfully demonstrated the power of hierarchical architectures and iterative optimization techniques for solving complex learning tasks, and their work continues to inspire and inform researchers in the field to this day. They showed that by combining multiple experts in a hierarchical fashion, it is possible to create models that are both accurate and interpretable.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.